Hello, I'm Mr. McBrien. This is TEJ3M Computer Displays. Today we're going to talk about monitors, a bit about video cards, and a little bit about ergonomics in monitors. Okay, so the monitor is the most common output device for most computers, and of course we have lots of synonyms for it: a display, a screen, a visual display unit if we want to get verbose about it. It's essentially an electronic visual display for computers. Now, originally computer monitors were used for data processing and television receivers were used for entertainment. Of course, these two concepts have merged largely with the advent of the 21st century. And so we can see this same kind of display doing work around both entertainment and real data processing. A monitor's not the only thing that influences the quality of the picture we see coming from a computer. We have the monitor quality, but we also have a video controller. These two things interact, and this gives us the quality of visual that we've become accustomed to. In terms of technologies, a lot of different image techniques have been used. Really, for the most part, cathode ray tubes, or CRTs, were the technology almost exclusively used before the 21st century. Nowadays, we see more of LCD monitors. We're going to talk about both of those, in part because the CRTs give us a good model for certain aspects of visual and give us really a good idea of where we came from as well. We can categorize our monitors by color output, and of course we'll talk a bit more about video cards in a minute, but they connect through the video card to the computer system. Now, the vivid colors that we see today weren't always the state of the art. A monochrome monitor was a very common thing to see, a cathode ray tube display. Through the 60s, 70s, and the 80s, monochrome was the technology that most people saw. And you'll still see them sometimes on cash register systems and other places where you don't need a rich interaction with the system itself. And in some cases we would see orange, sometimes white. Probably most common we'd see green screen for monochrome monitors. And those disappeared in the mid-80s. But certainly schools in the 80s, you could easily see computers like these ones with green screens and in fact very small displays as well. Now, as people were realizing they needed a richer interface with their computers, they began to look at any way possible to try to give you a little bit more information from the screen. This is where we got to grayscales. They were a special kind of monochrome monitor, and they could display shades of gray. And this was an amazing innovation. So essentially they were black and white TVs, and you could have a pretty good black, making it all the way up to white at the strongest end of the scale. And what's interesting about that was those grayscale monitors really only had 16 different shades of gray that were available. But using that, you could see some displays that were almost startling in those early Macintoshes. So you could see subtleties in the screen that were impossible before that. Okay, and then we move into the world of color. And of course, we see color monitors working exactly like monochrome monitors. The only difference is that you've got 3 electron beams instead of 1. And so it's with these in mind that we're going to dig more deeply into how those monitors work. So the three electron guns, each one has its own color, and we can add those together. So we have one red beam, one green beam, one blue beam, and it's worth noting that those beams aren't colored, they just hit a specific phosphor dot on the screen. So, unlike the case with monochrome monitor, each pixel contains 3 phosphors: a red phosphor, a green phosphor, and a blue phosphor. And we arrange those in a triangle. When we add them together, we can actually get real colors. Okay, so this is a cartoon of what that monitor, of its layout. So we can see a phosphor dot for red, one for green, and one for blue. And so each one of the pixels is represented by 3 phosphor dots. So this group is 1 pixel. And the electron guns are so accurate they can hit their own specific dot, their own specific phosphor dot. And mixing of colors, we go back to preschool and talk about pure red mixing with green to give yellow, mixing with blue to give magenta, and green and blue mixing to form cyan. And if we mix all 3 together in equal intensities, we get a white. Alright, so we talked about an electron beam. Another word for the electron beam is the cathode ray. And its history goes back 160 years now to when they had when Heinrich Geissler created the first good vacuum pump. And he was able to make tubes filled with a vacuum or filled with nothing. And Sir William Crookes then used those to produce the first cathode rays. So the history of our cathode ray tube monitors begins in 1855 with the mercury pump. And eventually it's demonstrated that we can bend those rays using a magnet. And we eventually display that they're actually particles because they have a negative charge. And in 1897, J.J. Thomson used them to discover electrons and begin the modern examination of the atom. So the physics, essentially what we can say is electrons will travel through a vacuum-sealed container from the cathode, the negative charge, to the anode, the positive charge. And so that's why they call them cathode rays, because they went from the cathode. They were a beam moving from the cathode. Now they're negatively charged, so they're repelled from the negatively charged cathode and attracted to the anode. And again, because they're charged, they can be the rays themselves can be turned using a magnet. And this is a cartoon of the cathode ray tube. We have a fluorescent screen on the right. We have the beam moving from the cathode, being focused by a focusing coil that's one set of magnets, being deflected by the second set of magnets and aimed using those. And again, the anode is positively charged. The cathode ray travels towards this. The cathode's negatively charged. The cathode ray travels away from the cathode. And here's a nice little cartoon of what we're seeing. The electron gun shoots away from the cathode, past the magnetic yoke, which guides the streams of electrons across and down the screen. And as the electrons hit the phosphor dots on the back of the screen, they glow. And this is what gives us the image. And in terms of how the image is developed, the electron gun scans left to right, top to bottom, and refreshes the screen one phosphor dot at a time. And obviously this does take time, and this refresh rate, we'll talk about that in a little bit. Okay, so some advantages of this old cathode ray tube. It's very bright, it has lots of colors, and good contrast. And another aspect, nobody wants them anymore. So if you're willing to use a cathode ray tube monitor, you won't have any trouble finding any. Okay, disadvantages, we know what they are. They're big, they're heavy, they consume lots of power, they're high voltage devices, which means there's a safety issue. Combining high vacuum and glass raises another safety concern. Then we talk about electromagnetic fields. Anytime you consume electricity, you emit EMF. X-rays, you can argue about the intensity of those, but also many people complain that those monitors result in headache and fatigue. And I may have mentioned, they're big and they're heavy. Okay, so let's get to some modern technology then. Let's talk about a liquid crystal display monitor, or the modern approach. These flat panel displays use liquid crystals to change light. And I say that carefully. They change the light. They do not emit light. Unlike those phosphor dots, they don't emit light. They actually block it. So before we go any further, let's talk a little bit about the history of the LCD. So again, we're starting our history in the 19th century. Liquid crystals were discovered by a botanist, actually. And then they largely sat on the shelf until RCA made the first experimental liquid crystal display in 1968. And quickly people saw the utility of this, and improvements have been moving pretty quickly in that 50 years. So around 1997, manufacturers began to offer full-size LCD monitors as alternatives to cathode ray tubes. But until recently, it was primarily on notebook computers and other portable devices that you'd see them. Little bit about the physics. So active matrix LCD displays, they depend on thin film transistors. And these essentially work much like a cathode ray tube in the sense that they're arranged in a matrix on a glass substrate. And they, again, use red, green, and blue, but we have a fourth transistor that provides opaqueness. In other words, it blocks some of the light. So, some of the advantages of this kind of approach, we know what most of them are. They're lightweight, they have sharp pictures, they have high peak intensity, the screens are perfectly flat. Ironically, now we're starting to look at curving those in the most expensive monitors. They're energy efficient. We can move them around very easily. They're actually easier on the eyes as well than cathode ray tubes. But they do have their disadvantages. The pixels are not absolutely robust. They will die, and you'll see discolored or black spots on your display. They have slow response times, something that really hasn't been addressed yet. And there are issues with a lack of versatility around resolution. Viewing angle, we'll still see examples of when you can't see from the side. Maybe the most interesting problem is with regards to cold weather. So liquid crystals are only liquid crystals if they're in liquid form, of course. And so we will see problems with temperature. Okay, moving on to monitor specifications. We evaluate the quality of monitors based on primarily 4 things: size, resolution, refresh rate, and dot pitch. We can talk about each of these individually very quickly. Size is the obvious one. So obviously the larger the monitor, the better we can see images. The only really important point here is that we measure monitor size typically in inches diagonally across the front of the screen. So a 17-inch monitor is 17 inches diagonally from one corner to the other. Resolution, pretty straightforward stuff here. We're all rather familiar with it, but the pixels, the number of pixels that we have on our screen gives us the idea of the resolution. And so we simply talk about a matrix when we talk about resolution. 680 by 480 resolution means there's 640 pixels horizontally and 480 vertically. And we can see various resolutions from the video controller. We can change this to a certain extent through the operating system, and there are given resolutions. What you will see, though, which is kind of interesting, is all things being equal, if your resolution increases, your image on the screen actually gets smaller. And if you think about that for a minute, you'll understand it. Okay, so resolution settings, I'd encourage you to play around with that a little bit and think about the aspects of this. And there's a little extension question for you to think further about it as well. Okay, in terms of standards, there's lots of different standards for monitor resolution. VGA being 640 by 480, Super VGA being higher, and virtually any color monitor you're going to get now will be high enough resolution to support Super VGA or greater. In terms of refresh rate, now this is a different aspect. Essentially, we can think of the refresh rate as the number of times that the screen can be refreshed per second. And the information on this slide is primarily targeted around the CRT. It in fact applies less towards the LCD screens, but refresh rate again is very important depending on what you're trying to do with the screen. If you're word processing, you don't much care. So it's measured in hertz again. No great surprise there. Cycles per second. And so what that means is if you have 100 hertz, it means that each pixel is refreshed 100 times every second. And I'd encourage you to think about the refresh rate of your eye. The actual refresh rate is up for debate. It depends on the effective refresh rate. Most people will report about 60 hertz for the refresh rate for your eye. So what it means is any refresh rate that is less than 60 hertz, and you'll start to see pictures or video appearing broken up. And you'll start to see objects not moving smoothly across the screen. And again, you have some level of control over your refresh rate as well through the operating system. Dot pitch is just simply the distance between same color dots. Ironically, these are usually referred to in millimeters after talking about monitor size in inches. And the smaller the better, essentially, and you should look for something less than 0.22 in a given monitor. Little cartoon of this. This gives us another picture of a pixel, then being three of our dots in a in a triangle formation, and our measure of dot pitch is just the center of one circle of one color to the center of the next. Now, something interesting, we talk about LED monitors versus LCD monitors, and this is a bit of a misnomer, and it's worth talking about for a few seconds. Again, I'll reiterate that liquid crystal displays do not produce light, and so any LCD screen has to be backlit. There has to be a light behind it to produce an image. And it's this backlighting, the type of the backlighting, that provides the distinction between LED and LCD monitors. So LCD, generally older technology, has full screen backlighting with cold cathode fluorescent tubes. Modern LED screens, each pixel is backlit individually with a white LED. And the difference between those two approaches is striking. LEDs are more efficient than fluorescents, but also the fact that you only light what you want means that your monitors, an LED monitor, is going to use considerably less power than an old style LCD. Okay, so some quick discussion of video cards. The first video card was in 1981, again from IBM, and of course it was monochrome back then. So something maybe a bit more modern. We can look at a fairly modern video card here with its onboard memory, heatsink, processor fan, and of course the connection to the motherboard. And we see the ports here, and we'll talk about the ports again in a few minutes. The video card, essentially it's its job to manage all of those pixels that we talked about, and to decide what to do with a video signal, decide what to do with each one of those, typically over 1 million pixels. And so what it does is it takes binary data from the CPU and turns it into a picture. Okay, and so really that's the key point there. It decides how to use pixels. It sends that information, once it does, to the monitor through a simple cable. And in addition to managing pixels in that way, it can actually measure 3D images. And so that graphics processor unit is really designed to manage geometry. It's designed to do the complex math associated with graphics rendering. And you'll see some cases where people have designed special applications that'll do calculations using the graphics processing unit, using video cards, that have nothing to do with video, but rather are interested in complicated geometric calculations. But the GPU, for its standard purpose, it implies less congestion on the system bus, and it allows the CPU to keep doing its standard functions with applications, and it takes care of all the complicated video requirements. Because of the fact that there's just a lot of calculations going on, remember, anytime we have activity, we can expect to see heat. And indeed, the best, most modern graphics cards have their own cooling systems associated with them. And no great shock, we've heard about the fact that if we don't have enough RAM in a computer, our video, hard video calculations can become difficult. Part of the way to deal with that is to have a good video card that has its own RAM, so it doesn't use the system RAM, it uses its own VRAM to do those calculations. And so we avoid having to upgrade the RAM on our computer by putting in a better video card. And some video cards now have, well, as of this point, a good video card can often have 8 gigabytes of RAM. Okay, connectors. We've seen many of these before, but it's good to collect them all together. So we have the old style VGA connector on this video card, a DVI connector, a standard that went away really pretty quickly, S-Video that really didn't catch on in the computer world very well, and then the modern HDMI video and display port, which has not become terribly popular at this stage, but has some advantages over HDMI. Okay, so VGA was around a long time, and we still see it a great deal. But there were problems, and that's why higher resolution systems will not use VGA. It doesn't shield electrical noise particularly well, and you can see image distortion and even sampling errors associated with that. Now, whether you're able to actually detect those problems, well, that depends on the resolution of your video signal. It depends on how good your monitor is, and it depends really on how good your eyes are as well. So speaking of eyesight, let's talk a little bit about ergonomics before we finish up. In order to avoid eye strain, it's a good idea to choose a good monitor. Make sure to place the monitor around 1 meter away from your face. Keep the center of the screen a little bit below the eye level, and try to arrange curtains and such that you can avoid reflected light. And remember the 20-20-20 rule. So every 20 minutes, look at least 20 feet away for at least 20 seconds. Little bit about EMF. That's a somewhat debatable point, but all electronic devices emit electromagnetic frequency noise. And depending on who you talk to, it's detrimental to your health. No sense taking a chance. Really, just, again, keep your computer at arm's length, again, that 1 meter. Take frequent breaks and use an LCD monitor rather than having a cathode ray tube monitor too close to you. Okay, so that ends the content portion of our discussion. A little bit about practical things. I'd encourage you to just mess around with your computer display settings a little bit. Make sure you know what they all mean, and change a few of them around to see what changes are caused in your display. You should have some fun getting them back to the regular settings as well. So to summarize, we've talked about different kinds of monitors and their uses. We've talked about cathode ray tube in some detail and LCD as well. Talked about video cards and done some practical discussion. To get an idea of the kind of size of calculations that are going on and the information that's being moved around, I'd encourage you to think about a data transfer rate in terms of megabytes. And so this will require you to do a little bit of an investigation, but have a look at a reasonably high resolution screen. Think about 24 or even 32-bit color and 120 hertz refresh rate. And I'd encourage you to just think about how much information is being transferred per second, per minute, or per hour. And I think it should give you some interesting things to think about. So in terms of references, you can look at some cathode ray tube information if you wish, and you may be interested to pause the video if you want and see a bit more about the history of the cathode ray tube. Thanks very much for your time. Have a great night.